Good morning.
Morning. Hello?
Hey, I'm here.
Hey.
I'm just making everything turn on. I see Autumn, Dylan, Ivy, Joseph, Mackenzie, Abby, and Grace. And oh, Autumn, you got in.
Yeah, my internet just came back on.
Oh, yay. Yay. Good, good, good. Okay. Like yesterday, if anything weird happens and all of a sudden you can't hear or something, send me a remind text and I'll check it and we'll all problem solve together. Yesterday, my math lab homework, that number 6, were y'all able to look at the example that I sent and basically copy it with different numbers?
Yeah, it was a lot easier.
The one that you had was a lot easier, or it was a lot easier after you saw the example?
Both.
Yeah, it was a bear. Sometimes I can't tell just by looking at a problem that it's going to be that ugly. You know, it looked pretty innocent to begin with, but yes, that one was nasty in the cleaning up. If you got it, very, very cool. All right. What do you need to ask me about? Let's start with 3.6 notes and video. If you have any general questions on the concept, and then if you have any questions from the homework, we'll look at those. Go. Which one of those 6 trig function formulas do you have to have memorized?
Arctangent.
Yes, and it's the easiest one. If I give you arcsine and arcsecant, then you should just remember that arccosine is the derivative of arccosine is the same as the derivative of arcsine with a negative coefficient, and the same thing for cotangent compared to tangent and cosecant compared to secant. We use all 6 of those formulas, especially the first 3 in Cal 2 a lot, and you end up having to get arcsine and arcsecant memorized. But at this point, if you just know the derivative of arctangent, that's good enough. I'd give you arcsine, arcsecant, then you know to attach the negative for the other 2. Does it make sense why if the slope of the tangent line at point F should be the reciprocal of the slope of the tangent line of its inverse? All the ordered pairs are just reversed. Mm-hmm. So if the derivative of the function is the change in y over the change in x, then for the inverse function, the derivative would just be flipped upside down because you've reversed all the ordered pairs. No general questions on the notes or video? All right. I don't have the 3.6 homework in my math lab, but I'll have it up there by noon. I'll do that as soon as I finish pre-calculus this morning. What do you need to see from the homework?
Number 29 was a bit of a bear.
Did you get it?
No.
Okay, let's look. Ooh, E. Ah, I see something good about that one. I like that one. I'm glad you mentioned it. Was that you, Joseph, that said this one?
Yes.
You're going to love it. I wish I was there to see you whack yourself on the head right after I tell you. Do you remember those, or do you remember me saying in pre-calculus, years ago now, eons ago, that some of my 2 favorite problems in pre-calculus were those that were simplifying expressions from calculus, because I knew how important that was going to be. And my second favorite problems in pre-calculus are those where you change ugly trigonometric and inverse trig functions to algebraic functions. it's pretty stunning to me that as scary as sine of arc cosine of t is, if we can change it to an algebraic expression, then I feel like I could handle it. Now, do you remember how we went about? Well, first let me say, you could do this as the sine of ugly, and the derivative of the sine of ugly is cosine of ugly times the derivative of the ugly. So it's completely doable that way. But do you remember how we changed sine of inverse something or inverse trig of trig into an algebraic expression? Anybody? Talk just a little bit louder. I can tell somebody's talking, but I can't hear what they're saying. I thought somebody was.
Oh. The way I did it, I drew a triangle.
Yes, 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 yes. You think the angle whose cosine is t, and you think, I don't know the angle whose cosine is t because I don't know what t is. So even though I don't know what this angle, let's call it theta or u, doesn't matter. I don't know what that angle is, but I can draw a picture of it. I can say there's an angle theta, and I can label a triangle in such a way that the arc cosine of theta is t. Now, what does that tell you about this triangle?
The adjacent side is t and the hypotenuse is 1.
Perfect, because because cosine is opposite over adjacent. Let me let Jacob in here. Good morning, Jacob. Jacob, can you hear me? Okay, he's probably listening and muted. All right, so now I have an angle whose cosine is t. How do I find what the sine of that angle is?
You got to get that last angle or side.
For sine, I need opposite over hypotenuse, so I have to find opposite by using the Pythagorean theorem, square root of hypotenuse squared minus other leg squared. So now, even though I don't know what theta is, I have a picture of what the angle theta looks like if it's the acute angle in a right triangle, and I can rewrite h of t in terms of this. If h of t is sine of theta, then that's opposite over hypotenuse. That's just the square root of 1 minus t squared. And then to differentiate it, write it as 1 minus t squared to the 1/2. How about that, Joseph?
Yeah, that's not where I was going with that one.
It's not where my first instincts would have taken me if I hadn't done this problem a million times. I would have taken the sine of ugly times I would have differentiated the sine of ugly as cosine ugly, and then the derivative of ugly, and it would not have given me an identical looking answer. It would have given me a trig answer, but I could have changed that trig answer to algebra and gotten the same thing that I would get this way.
Mm-hmm.
You think you could finish that one now, Joseph?
Yeah, I can get it.
Okay, cool. All right, does anybody have another homework problem?
I worked 33 like 2 times, and I checked all my work, and I just don't know what I did wrong.
Okay. Trying to think.
I don't think I'm simplifying it to what the book wants, but I don't know how to get there either.
Okay. I'm trying to think if there's a quick way for y'all to show your work on some problems. Hey, what if you held it up to your, are you on a phone or a laptop, Ivy?
I'm on a phone.
If you turn video on and pointed your phone at your paper, would it suddenly appear to us?
I could try.
Yeah, I'm just curious to see if this works. If it doesn't, it's okay. But that would be cool if it did work.
Okay, if you see me in PJs, then I'm sorry.
Point your phone at your paper before you turn on the video.
Well, yeah, but there's 2 cameras on a phone.
I saw a red block. Hey, I see your work. Let me see if I can make it big.
I can't see where it's pointing at, so hopefully this is right.
Okay, we're just trying this. It may not end up working very well. I'm trying to see how to make it. Oh, show small active speaker video. That wasn't it. Oh, I'm just trying to make it bigger. Show thumbnail, show grid. I may not. Oh, that did something. You know what? I can see number 33 beautifully. Bring it down just a little bit. Just turn your phone, flip it up toward the top of the page. And I promise we're not going to spend long trying to work this out.
I can't really see my camera this way either, so I don't really know what I'm pointing at.
I think this is going to, ooh, it comes into focus and then goes out of focus. This might be too cumbersome to try via Zoom, but anytime you want me to look at your work, just send me a picture of it via email and I will be happy to do that. Let's go ahead and work this one. Number 33. Why? Yeah. All right, there it is. So I need to find the derivative, and I know I can find the derivative term by term, and the derivative of the first term, I'm looking at this as natural log of ugly. So what's the derivative of natural log of ugly?
1 over ugly.
And what does 1 over a fraction do to the fraction?
Just flips it.
Okay, so 1 over ugly would just be x minus 1 over x plus 1. And then what else goes into the derivative of natural log of ugly?
The derivative of the ugly.
And that's going to take the quotient rule, right?
Mm-hmm.
So denominator, derivative of the numerator is just 1 minus the numerator, derivative of the denominator is just 1, all over the denominator squared. And that should be the derivative of the first term. 1 over ugly times the derivative of the ugly. And then what's the derivative of arctangent x?
1 over the ugly, or the derivative of the ugly over the ugly, something like that.
Okay, 1 over 1 plus ugly squared times the derivative of the ugly, and the derivative of the ugly is just x. I'm sorry, the derivative of the ugly is just 1. So that's what you had for the derivative before you started cleaning it up, Miss Ivy?
I'm checking 1 sec.
Okay.
You know what? I think I did something stupid.
Oh no, what was it?
When I was doing the Lodi high, Heidi low, I did it of the flipped fraction and not of the actual ugly.
Oh, and once you've done that once and you keep looking at it over and over, your brain does the same thing every time. It's hard to find your own mistakes. It's much easier to find somebody else's mistakes. So you could clean that up now?
Yeah, I think I could do it now.
Awesome. All right, what else? Any other questions?
On number 19, I got a different numerator, and I don't know what I did.
Okay. Let's see. The reason y'all only have to memorize the derivative of arctangent is I can't keep the other two in my head. I can memorize them right before a test. I can memorize them for a short amount of time. And y'all's brains are probably much more flexible than mine at this point. But I just have to keep rememorizing the derivative of arc cosine and the derivative of arc secant. In Cal 2, I use them enough to remember. Cal 1, I keep having to look them up. So this is the derivative of a constant times a function. I can just keep up with the constant and take the derivative of the function, and this is arc cosine of ugly. So the derivative of arc cosine of ugly, the way I read this is -1 over square root of 1 minus ugly times the derivative of the ugly. The derivative of the ugly just ends up in the numerator. So 1 over square root, or -1 over square root of 1 minus ugly squared times the derivative of the ugly. What's the derivative of the ugly there? Did you use the quotient rule on it?
Yes.
Okay. You don't have to, you can, but you have to train, or save you a lot of work if you train your eyeballs to see x over 2 as 1/2 x. Isn't that the same thing?
Mm-hmm.
So what's the derivative of 1/2 x?
1/2.
Yeah. Is that what you got by the quotient rule?
That's what I got.
Yeah. But was this easier?
Yeah, it's a lot easier.
Okay. All right. Yeah, you should get the same thing, but we're looking for time-saving things we can do. All right. So on a test, in person, which we may never have again, that's partial credit. You've done the calculus correctly, but this is a little bit ugly to clean up. Tell me what you first did. I'm going to say 3 times -1 times 1 is -3 in the numerator. Wait, actually, you said you got a different numerator than the answer?
I know what I did.
What did you do?
I forgot to multiply by 1/2. Like, I found the derivative, and then I guess I just forgot to use it.
Okay. All right. That's where always making sure that every line's equivalent to the line above it. Actually, no, that wouldn't have helped you because that was your first line of the derivative. There was no equivalent to the line above it. Just in case anybody had trouble with that denominator, tell me how you cleaned up that denominator. That looks like the harder part to me.
I'm looking at mine and I honestly can't remember how I did it.
Well, if you need to, put in baby steps. You don't have to be able to do many things at once. I'd probably look at it and say, well, that 2's in the denominator. I can put it out in front of the radical in case that helps me. Sometimes I'm just stalling to give my brain a minute to work. So I do something as simple as, well, let's just put that together as a single fraction. And let's get rid of those parentheses while we're at it. Then what?
I took the 2 and I put it back into the radical.
Just you distributed it and got 2 minus x squared over 2?
No, I squared it before I put it back in.
Yes. What you have to think of that 2 as being, since you know you can't just distribute a constant through a radical, you can think of the 2 as square root of 4. Is that the same thing?
Mm-hmm.
And then you can say, when I multiply 2 radicals, I can multiply their radicands. I can say square root of, or I can say 4 times 1 is 4. And I can say 4 times the second fraction would just leave me -x squared. Is that okay now?
Yeah.
All right. What else? I haven't heard from any of my men. Y'all have any questions?
Take offense to that, Miss Miles.
I'm sorry. Oh, yes. I did hear from one of my men. I'm sorry, Joseph.
Poor Joseph.
No. I forgot about hearing from Joseph. I apologize. All right. Anything else? If not, then let me just preview something real quickly. I know y'all may not have, probably haven't watched the video on this yet, but I want to tell you something about 3.7. Ooh, y'all got my email on the most helpful way to email me your work on a problem? If you'll tell me where it's from and write down the original problem and number the steps so I can say, oh, in your step 5, blah, blah, blah. Y'all will do that for me, won't you?
Yes.
Yes, ma'am.
I know you will, because you're awesome. And New York folks, you should have gotten your refund by now. I got mine. Have your parents check your bank account and make sure there are refunds in there for the canceled trip. Shoot. Let me grab something real quickly. I didn't bring 3.7 in here. .7, if you haven't looked already, it's word problems. There are 2 main kinds of word problems that we have in calculus. 3.7 is related rate problems, and then 4.7 is optimization problems. And you can already guess, if I give you, just talking about the optimization problems for a minute, if I give you a quadratic equation, let's say that represents profit, and I say what number of units will maximize the profit? If the profit function is a quadratic function, how do you find the x value that maximizes it?
The vertex?
Yeah, it's going to be the vertex. The vertex of a concave down parabola is going to be a max, and the vertex of a concave up parabola is going to be a min. Now, that's fine as long as I only give you a quadratic equation, but if I give you some squarely 10th degree equation, how are you going to find what maximizes or minimizes it?
Wouldn't you just want to go like as far to the left or the right as possible?
But what if it went up on both ends? There's not going to be in this case, there's not going to be an absolute max because it's going to keep increasing forever. But if I wanted you to find the absolute min for that function, let me make it a little less squirrely. How could you find the absolute min for that function?
Find the derivative equal to 0.
Right. The absolute min would have to occur at one of these high points or low points where the tangent line is horizontal. So you could just find, you could find those 3x values where the tangent line is horizontal, and then you could check each one of their y values and see which one's the lowest. It would end up being this one in that problem. So that's the optimization problems. But 3.7 is related rates, and it does make sense that how I started saying in calculus, but in life, some problems have, or some quantities have related rates. If, for example, this is page 182 in the book, if you have water that is dripping out of a cone, how fast the radius is changing is going to affect how fast the height is changing. Or how fast the height is changing is going to affect how fast the volume is changing. So that's what's meant by related rates. The rate of one thing affects the rate of something else. Now, if you start with the volume of a cone formula, and you're not going to have all these geometry formulas memorized, I'll give you what you need. Or if you're taking a test online, you can look it up. If I give you the formula for volume of a cone, then you can find an equation for the rate of change in volume relative to the rate of change in height and the rate of change in radius. In other words, you can take the derivative of both sides of this equation with respect to time, because that's what a rate is. It's how fast something is changing. Now, if I had just given you this formula yesterday and said, differentiate this, you probably would have used the simple V prime for the derivative, but V prime doesn't tell what you're differentiating with respect to. So rather than using V prime, I'm going to say dV over dt. That's the symbol for the derivative with respect to time. And since the radius and the height are both functions of time, and what I mean by that is the longer the water's been dripping, the lower the radius, or the smaller the radius and height are going to be. They both depend on time. So when you differentiate any variable that depends on time, you use dt in the denominator. This is the change in height with respect to time. This is the change in radius with respect to time. So look how you take this derivative. You say the derivative of volume with respect to time is dV over dt. And then what's it going to take to differentiate this expression? Since it's r squared times h, what are you going to have to use?
Product rule.
You're going to have to use the product rule. You could just keep up with the pi over 3 because it's a constant, but then you have the first factor, r squared, times the derivative of the second with respect to time, plus the second factor, h, times the derivative of the first with respect to time. The derivative of r squared with respect to time is 2r dr over dt. And notice really we're using implicit differentiation here. We're saying we know that volume, height, and radius are all functions of time. We don't know the exact expression for how radius relates to time or h relates to time. So there's some uglies that we can't define explicitly. That's why whenever we differentiate them, we have to have dH over dt or dr over dt as part of the derivative. From that equation, you can see that the rate of change in volume is related to the rate of change in both the height and the radius. So what we're going to be doing in all of these problems, there's a good little box at the bottom of page 183. Well, actually, let's just work our way up to that for a minute, and you may be able to fast forward through part of the video, but somehow I feel like if we talk through a few examples together, it might be more helpful than just watching the video on this. Let's look at this example 1, and then we will talk about the box at the bottom of page 183. Example 1 says, suppose that x and y are both differentiable functions of t. Hey, what does that mean? How? It says they're both differentiable functions. Well, what could make them not differentiable? Isn't everything differentiable? Search your brain for, you can't find the derivative where what happens on the graph?
It has unbounded behavior.
Unbounded behavior. No.
There's a discontinuity.
There's a non-removable discontinuity, A discontinuity you can't fix just by filling in an open dot. When else have we not been able to differentiate? What's an indicator on a graph? Hey, the graph's not going to be differentiable here.
Asymptote.
That's true. The function would not be differentiable at an asymptote. And actually, whoever said unbounded behavior, I get what you're saying now. At an asymptote, the graph would be going unboundedly to positive infinity or negative infinity. You're right. I wasn't thinking about that example. I was thinking something about the absolute value function. Where is it not differentiable?
Oh, at a sharp turn.
Yes, yes, that's the things that we look for in a graph. We know the graph's not differentiable where there's a sharp turning point, where there's a non-removable discontinuity, and actually that covers asymptotes. Vertical asymptotes are non-removable discontinuities, so those are synonymous. And then the other thing is when the graph oscillates so wildly between 2 points that you can't pin it down. All right, so if x and y are both differentiable functions of time and are related by that equation, find the change in y with respect to time when x equals 1 if I give you this other rate. If you have an equation where 2 of the variables depend on time, you have to give me one of the rates in order for me to find the other rate. So the rate that we're given is that the change in x with respect to t is 2 when x is 1. All right, so this is just a parabola. Play like this is a marble rolling along a parabola. And dx over dt would be how fast the marble is moving horizontally. dy over dt is how fast the marble is moving vertically. And how fast it's moving horizontally or how fast it's moving vertically depends on how fast it's moving horizontally. When you differentiate both sides with respect to t, we can't just use the symbol y prime because that doesn't indicate that we're differentiating with respect to time. We have to say dy over dt is the derivative of x squared times dx over dt. And then you tell me at what x value you want to evaluate this expression, and you tell me the value of dx over dt, and it's just substitution. If x is in centimeters, then when the marble is 1 centimeter from the origin, this is how fast the y's are changing. This is the slope at the point where x equals 1. Now, to me, these problems actually make more sense when you know what the x and the y are about, when you're actually dealing with a word problem that is meaningful. And for that, here's example 2 in the book. A pebble dropped into a calm pond causes ripples in the form of concentric circles. We've all seen that before. The area enclosed by each circle depends on the radius of each circle. Does that make sense? Area depends on radius? Everybody say yes.
Yes.
Okay, area depends on radius, and radius depends on time. How big that circle is depends on the number of seconds since the pebble was dropped into the water. So the radius depends on time, the area depends on time, the area depends on the radius. There's all kind of relationships we could define there. But the area of the circle is given by a equals pi r squared, and we know that r depends on time. And this is telling us the relationship between the radius and the time. The change in radius with respect to time is 1. Can you tell me what the units on that 1 are? What the heck is that 1? Look at this symbol.
Would it be like feet per second?
Absolutely, because the radius is given to us in feet and the time is given to us in seconds. So that dr over dt is how fast the radius is changing. It's changing at 1 foot per second. Now, you give me the equation. You give me one of the rates so that I could find the other rate, and it's going to be at some specific radius. Now, that reminds me of something I wanted to say about this picture. Y'all have probably seen water flow out of a funnel, and up here, when the funnel is full, the height goes down slowly, but the further the height goes down, the faster the radius starts getting small. That's not exactly how I wanted to say it. Let me think. If this was huge, imagine a conical swimming pool or something. If you're watching a huge conical swimming pool drain, then for a while, it's going to be lowering slowly, but after some point, it's going to start lowering in depth faster and faster because that radius is getting smaller and smaller. The rate at which the height is changing doesn't stay the same for the whole funnel. At the top, when it's full, it's draining slowly. The rate at which it's draining is the same, but the rate at which the height is changing changes. It's the height, it's lowering slowly when it's full, but when it gets down here, it starts circling the drain and draining very quickly at the bottom. All I wanted to say about this picture was that change in radius or the change in height is not constant. They both depend on the height of the water at some particular second. Now that just was not beautifully explained. I feel like that's one of the times if I could see your face and you could see mine, we'd be communicating better. That's not really a possibility. So let's go back to example 2. I feel like
I have a question.
Yes.
Is the change in radius, is that counted as constant?
Yeah, I knew I wasn't saying that precisely. The change in radius is a constant. No. Actually, it's not. Again, the radius is going to be changing a lot faster when the cone is almost empty than it is when the cone is full. And that's why we have to be given in this problem, example 1, that we really didn't know what it referred to. We were given a change in x with respect to t is 2, but notice it says when x equals 1. That's just how fast the x is changing at that moment in time. At some other moment in time, that rate would be different. I feel like I did just a little bit better with that, Miss Ivy. Do you understand what I'm saying?
I'm still a little confused, but it's okay. It's not that important.
Well, it's pretty important. Yeah, actually, it's very important.
Oh, no.
Let me tell you why it's important. If the change in y was a constant, then we wouldn't need this when x equals 1. We would just find the change in y with respect to t. Y could be, say, the height of the water, and it would be the constant whether the cone was full or the cone was almost empty. But we've all watched something drain before, and we know that height, once you get down to half a cone or a third of a cone or fourth of a cone, the closer the water is to the bottom, the faster the height starts decreasing.
I understand the thing about the height. I just, like, the radius isn't clicking with me because I see 2 straight lines and I'm like,
All right, but if the change in height is not constant, that's because the change in radius is not constant. The radius and the height are directly related to each other. So if the change in height is not constant, the change in radius is not going to be constant. The radius is shrinking a lot faster down here than the radius would shrink up here.
Okay.
I can kind of picture that because I've watched water drain out of a funnel or the bathtub. Actually, I've filled up a swimming pool before, and our swimming pool in Grassy Cove had a deep end, and it seemed like the deep end filled up very quickly because it was only about half of the pool. But once you got beyond that slope, and it was filling up the entire length of the pool, it took forever to fill up because the radius or the length that it was filling up was much more.
Mm-hmm.
All right, keep mulling that over. Keep thinking of that. Let's go back to this example 2 now. We have, notice this one, the rate of change in the radius is 1. That is a constant. They didn't say the rate of change in radius is 1 at 2 seconds or at 5 seconds. It just says the rate of change in radius is 1. That's how fast the radius of the circle is growing. And if we're asked to find at what rate is the total area changing, you have to know what symbol that's asking you to find. The rate at which the area is changing is going to be dA over dt, the change in A with respect to time. So we're going to say we're looking for dA over dt when R equals 4. This is the equation we know to use for area of a circle. This is the rate we're given. This is what we're looking for. So take that equation and differentiate both sides with respect to t. Is this right-hand side going to take the product rule? To differentiate it?
No.
No, because pi is a constant. You can just keep up with the constant and differentiate the r squared. The derivative of r squared would be 2r, and there's our constant. And then because radius is a function of time, we also have to have a change in radius with respect to time. After we've differentiated both sides, then we just plug in 4 for the radius, 1 for the change in radius with respect to time, and this is how fast the area is changing at 4 seconds. All right, so this is where we'll wrap it up for today. This gray box is the steps that we're going to use precisely. We're going to identify all given quantities and quantities to be determined. We're going to say, if you give me, let's see, the radius is increasing at a constant rate of 1 foot per second, I have to know what symbol to use for that. It's a change in radius, so it's dr, and it's with respect to time, so dr over dt. And once we write that down, we identify what we're looking for. And that's number 1. Number 2, write an equation involving the variables whose rates are either given or are to be determined. We needed a formula that had r's in it and a's in it, because this is a rate we're given, this is a rate that we're looking for. And we know a formula that relates r's and a's in circles. So we write down the equation, a equals pi r squared. That's step 2. Step 3, differentiate both sides with respect to time. Step 4 is very, very important. A common mistake in this section is that people want to substitute in, let's say, this 4 seconds way too early. If you just put it 4 seconds in the place of R there, then all you're finding is the area at 4 seconds. You don't need a rate at all to find the area at 4 seconds. You don't substitute the 4 until after you've differentiated both sides with respect to time. So in step 3, we're actually in step 2, you're going to have an equation that involves all the rates that are either given or to be determined. In step 3, you're going to differentiate both sides with respect to time, and not until after you've done that are you going to substitute in the values to find the rate of change that you wanted. All right, that's all I'll try to say about 3.7 via Zoom. If that all made sense, you can fast forward past it on the video. If it didn't make sense, you can watch it again. But let me think for a second. We have 2 days on the calendar, the revised calendar on the syllabus amendment, to do 3.7. So today I'm going to put 3.6. 3.6 homework in my math lab. Let me tell you, oh, that was good timing. Let me tell you where to stop watching in the videos on 3.7, the problems that we'll talk about tomorrow. Hold on one second. 3.7 for tomorrow. I want you to watch the video and try examples up to number 25. We're talking about 3.7, attempt 1 through 25. After you do 3.6 homework in my labs tonight. Got it?
Okay.
All right, if you have any questions, because I stutter sometimes, if you have any questions, just email me and I'll clarify. Oh, one last thing. Y'all, you're more proficient at typing on your phone than I am. It takes me forever to send a text in Remind because my big fat fingers just fumble all over the place. If you have a long involved question, anything that's not answered with a yes or no, email it to me instead of sending it to Remind. I just type so much faster on my laptop than I do my phone. So email me instead of Remind. You can send me a Remind that said, hey, I sent you an email, but that's probably not necessary because I get notifications for email on my phone. Alrighty, y'all have a good day. I appreciate you.
Okay, bye.
Bye-bye.